Today, we're going to tackle a question that you see sparking just endless debates online: cooling a really powerful computer or maybe even a whole data center up in orbit. You've got some people saying, oh, it's easy, space is super cold. And then you have others who say, no way, it's impossible, space is a vacuum. So, which one is it? Let's dive in and actually figure out the real answer by doing the math ourselves.
So, here's our game plan. We're going to start with the debate itself, then get into the fundamental physics that really governs all of this. After that, we'll add in some real-world problems, like the sun and the earth. We'll run the numbers for the best and worst-case scenarios, see what happens when we try to make things bigger, and finally, wrap up by looking at what this all means for the future of industry in space.
All right, let's frame the central argument. On one side, you have this really intuitive idea that, hey, space is freezing, so heat should just go away. But on the other side, there's the hard reality that a vacuum robs us of the two main ways we cool things down here on Earth.
I mean, it's a super common thought, right? The background temperature of the universe is just a smidge above absolute zero. So if you have something hot, shouldn't that heat just, vanish into the cold? Well, turns out it's not quite that simple.
Here are the two sides laid out. The easy argument is all about that huge temperature difference. The impossible argument, which is correct, points out that here on Earth, we rely on conduction and convection. That's transferring heat by touching something or by moving air or water around. In the vacuum of space, those two are completely gone. So what are we left with? Well, we have only one tool in our toolbox: thermal radiation. Every single object with a temperature above absolute zero radiates energy. And in space, it's not just an option, it's everything.
So to really get this, we've got to move past the arguments and look at the actual physics. We're going to use first principles here to calculate just how much cooling we can actually get. And believe it or not, it all comes down to one key equation. And here it is, the Stefan-Boltzmann law. It sounds complicated, but it's a surprisingly simple and incredibly powerful rule. It tells us exactly how much energy a surface gives off just based on its temperature. You know how a hot piece of metal glows red? That's this law in action. This is the foundation for solving our entire problem. Okay, let's break this down real quick. P is the power, the heat you're getting rid of. A is just the surface area of your radiator. That little epsilon is called emissivity. It's basically a score from 0 to 1 of how good a surface is at radiating heat. A perfect black surface is a 1. Sigma is just a constant that makes the units work out, but the absolute hero of this equation is T, the temperature, in Kelvin, raised to the 4th power. This T to the 4th thing, it's everything. It means even a small increase in temperature gives you a massive boost in cooling power.
So, let's run a quick calculation. Let's say we have a satellite that's generating 20 kilowatts of heat, maybe from a bunch of GPUs. If we want to keep it at a nice, comfy room temperature, say 20 degrees Celsius, the math tells us we need a radiator that's about 50 square meters. Now, since a flat satellite has two sides, that's a body of about 25 square meters. And what's crazy is, that's almost exactly the size of a SpaceX Starlink satellite. So right off the bat, we're in a very realistic ballpark.
And this chart just shows you the magic of T to the 4th so perfectly. At 20 Celsius, 1 square meter of radiator gets rid of about 420 watts. But if we let that radiator get hotter, say to 80 Celsius, which is totally fine for most computer chips, the power it radiates more than doubles to 880 watts per square meter. That means we can dump way more heat with the same size radiator. That is a huge engineering advantage.
Okay, but a satellite isn't just floating around in a cold, dark void, right? It's also getting blasted with energy from its neighbors. To get a real answer, we have to think about the heat coming in, not just the heat going out.
And these heat sources are no joke. Direct sunlight is slamming the satellite with over 1,300 watts for every square meter. Then you've got sunlight reflecting off the Earth, which can add another 450 watts. And finally, the Earth itself is warm, and it radiates its own heat, adding another 200 watts or so. So our cooling system doesn't just have to handle the computer's heat, it has to beat all this incoming energy too.
Okay, now we have all the pieces of the puzzle. The heat our computer makes, the heat coming from the outside, and the equation for getting rid of it all. So let's put it all together and see if this thing actually works by looking at two very different but very real scenarios.
So the best case scenario is all about flying smart. You orient your satellite so its big, flat radiator surfaces are always edge on to the sun. This gives the sun the smallest possible target to hit, which minimizes how much heat you absorb while giving radiators a nice, clear view of deep space to radiate heat into.
So let's walk through the thermal budget. We start with our 20 kilowatts from the computers.
Then we add the heat coming up from the Earth, which for our Starlink-sized satellite is about 8 kilowatts. That means we need to get rid of 28 kilowatts total. But remember, our radiator running at 80 Celsius can ditch 34 kilowatts. And the result? We have a 6 kilowatt cooling margin. It works. And we've even got some room to spare.
But what if you can't stay in that perfect orientation? What if your mission requires one of the big flat sides of your satellite to always face the sun? Maybe for a solar panel or an antenna? Well, that is the worst-case scenario.
And this right here is the critical problem. Even if you cover that sun-facing side with super reflective material, the real issue is you've just lost half of your radiator area. That entire surface is now just fighting to survive the sun's heat. It can no longer help cool the inside of the satellite. It's completely taken out of the game.
This table really makes the trade-off crystal clear. In the best case, with both sides of our radiator working, the thermal budget is balanced. The design is simple. But in that worst case, we lose half our radiator area, the whole system overheats, and we're forced to add extra deployable radiators, these things that unfold like wings. That adds mass, complexity, and a ton of new ways for things to break. The physics is the same, but the engineering challenge just got way, way harder.
So we've pretty much established that cooling a 20 kilowatt computer is a solvable problem. But what happens when we try to scale this up? Because the real dream here isn't just one computer, it's entire racks of them pulling 100 kilowatts or more. This is where we stop talking about a physics problem and start talking about a really serious, complex engineering challenge.
And at that kind of scale, a whole new set of problems just pops up. It's not just about radiator area anymore. Now you need to actively pump hot fluid out to those big radiators. And guess what? Those pumps need power. The coolant fluid itself adds a ton of mass. You have to fight against the fluid's thickness and all the pipes. The inertia of all that liquid sloshing around can actually mess with the satellite's pointing. You even have to worry about your coolant freezing when parts of the system get cold. It all adds up, and it's why engineers are trying to design computer chips that can just run hotter to begin with.
So after all this analysis, let's zoom out. What does this all mean for the big picture? I mean, we're not just doing these calculations for fun. We're asking a really serious question. Is it actually feasible to move one of Earth's most power-hungry industries, data processing, into space?
And here is the crucial takeaway from the source material. Despite all those engineering challenges we just listed, cooling these systems does not require some magical sci-fi technology we haven't invented yet. The basic satellite designs we see flying today, like Starlink, are already in the right ballpark. We have the foundational tech to make this happen.
So, the final verdict is in. Is it easy? No. Is it impossible? Absolutely not. Cooling in space is fundamentally a solvable engineering challenge. It's a game of trade-offs. It's a constant balance between temperature, radiator size, orbital position, mass, and complexity. It's a design problem, not a physics barrier. And why does this all matter so much right now? Well, because with the explosion in AI, data centers here on Earth are consuming the power and water of entire cities just for cooling. The first big industrial move off our planet might not be making things or mining asteroids. It could very well be massive swarms of AI servers crunching data in orbit, powered by endless sunlight and cooled by the endless void of space.
And that leaves us with one last thought. We've shown that cooling powerful computers is within our reach, but this might just be the warm-up act for the next, even greater challenge, figuring out how to cool multi-megawatt nuclear reactors in space. You know, the kind of power we'll need for real deep space exploration and building colonies. Now that is the next frontier.